Is the screen visible?
Yes, sir.
Sir.
Is it moving?
Yes, sir.
Okay, so that is fine then. So now I come to the last topic in the third chapter of your book. A very interesting geometric topic. It is called Vertex Theorem. So this is going to be a somewhat short. Nevertheless, what I am going to do is not the proof that is given in the book, but something different. The book says it is writing a, it's giving a stating and giving a proof of the result, which I am going to generalize here and give you a general proof. So I will also tell you the historical background of this one. So let us begin. In this section, we have to do with the signed curvature of a curve, of a plane curve. Since I am not going to do with the ordinary curvature, so signed curvature I have denoted by k suffix s. So instead of that, I will just write it as k only. K suffix x will be denoted by k. The actual k was modulus of k suffix x, if you remember. So that is the difference in the notation. It's just for the sake of simplicity. Every time I don't have to write k suffixes. Since we are dealing with more than one curve at a time, I may have to indicate what is this k for. So if gamma is the curve, I may have to indicate k gamma. Okay, suppose the k gamma 1 is there, then I have to write k gamma 1. K of what I have to write. So because of that burden, instead of writing this s, I have dropped out the s, that's all. So sometimes I have to write k gamma for to indicate which curve I am talking about. Okay, so we are dealing with the signed curvature of plane curves. The first I give you some local geometry of curves, which is again intuitively clear, but it needs a proof. Everything needs a proof. And it is a very nice thing. You may not see it in the book at all, or maybe it is there somewhere hidden in the exercise. Take f1 and f2, two smooth functions defined on a closed interval. Take any point in the interval at which the two functions agree. f1 is equal to f2. And the derivative is also 0 at that point. Suppose further that f1 is always bigger than or equal to f2 in a small neighborhood of this point C. Okay. Now you look at the graph of these curves. What is the graph? Graph is consisting of t comma ft, right? T comma f1t is the graph of f1. T comma f2 is the graph of f2. Okay. Look at the graph of these functions. Okay. Remember f1 of c equal to f2 of c. Okay. Therefore, the two graphs will pass to the same point, right? C comma fc is a common point. And the derivative there is 0. So what happens? The x-axis becomes a tangent to the curve at that point. Okay, because derivative of the function is 0, right? The tangent to that curve will be x-axis. So this is the picture. So what is the conclusion? If kappa I, is there are two curves, right? So I have to write kappa I of gamma 1, kappa I of gamma 2. So kappa I am writing. Kappa I of denotes the signed curvature of the graph Fi. Okay. Then kappa 1 at C is bigger than or equal to kappa 2 at C. F1 is bigger than F2 in a small neighborhood, then the kappas will be bigger than kappa 2. If you draw the picture, okay, what happens? At a point, both the curves have x-axis as a tangent. So both the curves will lie above the line there, parallel to the x-axis, right? Which one lies above? F1 will lie over the graph of F1 will lie over f of F2. So that curve has a higher curvature than the lower curve gamma 2, right? So this is, heuristically, layman wise, it is obvious. What is the proof? So it's a one-line proof here. Though I have made all the preparation, that is why it's one-line proof. Okay. We have computed remember, we have computed the curvature of a graph. Okay. You use that formula, then this will come very easily. So here is the proof. For the function x to x comma fx, the signed curvature of this graph k of gamma f. F is the function, gamma f is the graph, k gamma ft. We have seen that it is equal to f double dot divided by 1 plus f dot square raised to 3 by 2. So this is the formula we have derived earlier. Now f dot is 0 by Taylor's expansion. F1t is bigger than or equal to F2t in a neighborhood implies the second derivative F1 double dot must be bigger than F2 double dot. Okay, Taylor's expansion at 0, at one's first point, they are equal, right? So Taylor's expansion, say f of, say you can write as c plus epsilon or any x, c plus epsilon, you put fc, f1c and f2c are equal. Then f dot, that part is 0. The second term is 0, right? The third term is f double dot times some epsilon. For all epsilon, if these two are bigger, okay, just use that property. The coefficient must be bigger than or equal to coefficient of this. Okay, so this is the coefficient of the third term there. F1 double dot. F1 double dot C must be bigger than or equal to F2 double dot C. If you are not convinced of this one, assume this is less than that one, then you will be able to find an epsilon for which the value will be smaller than that. Rigorously, you can prove that. Okay, the first non-vanishing term in the expansion, okay, in the expansion determines the sign of a curve, sign of the whole thing in a small neighborhood. So this is the elementary analysis of Taylor's expansion. Since the first term for both of them are equal, namely the 0th term, the second term, the first derivative is 0. It is the second derivative which determines the sign. Okay, so this will be always 1 for 1 bigger than this one. If you take the difference of this one, f minus t, sorry, f1 minus f2, that's positive. So you can apply the theorem for a difference here, this will be positive. This f dot is 0. So the numerator here determines the sign of the kappa. Okay, this f dot is 0 for both of them. Okay, f double dot will determine it. F double dot will be bigger than f dot. So the same thing as kappa is bigger. Kappa 1 is bigger than kappa 2. Okay. The following corollary is used repeatedly in whatever I'm going to prove now. Okay, in the proof of that, we are going to use this repeatedly, often not even mentioning perhaps, if you grant. Gamma be a simple closed regular curve in the plane oriented counterclockwise. Since we are talking about plane curve, this makes sense. Okay, let C be a circle such that gamma is completely contained in the closed disk bounded by C. So the curve is inside the circle. Okay, in the interior of circle, but it may touch the circle also. Okay, in the closed disk bounded by C. Suppose P is a point of the intersection. What does this mean? That P at the point P, the circle touches the curve gamma. Okay, suppose P is a point of the intersection of gamma. Then K gamma at P is bigger than or equal to Kc at P. Of course, Kc at P we know. This will depend upon the radius of the circle C. Okay. So Kc at P is a constant. Kc is a constant, but K gamma can vary, and that will be always bigger than this one. At all the points wherein the circle touches the curve. So this is the corollary. So how do you go about that? All that you have to use is this lemma modulo our, maybe you can say that every manifold is a graph of a function, right? What do? You look at the tangent to the circle, right? Turn it around, turn the entire figure so that this tangent becomes horizontal. Then in a small neighborhood, this is what we have done in the last lecture, that every manifold looks like the graph of a function, right? So this is how we have to do that. So turn it around so that it becomes the tangent is horizontal. Now what you have? You have the circle, okay, contained, let us say the x-axis is the tangent now. You can assume that P is 0, 0, okay, by changing the coordinates. So you have circle completely contained in the above the x-axis, touching the x-axis. The curve is also there, but it is inside the circle. So if you look at the graph of the circle and graph of the curve, what you get? The graph of the curve has always value. Now, the function which defines the graph, okay, the function is always bigger than the function which defines the circle. Okay, the y coordinate is bigger than the y coordinate of the circle. That is how it will be inside the circle. Okay, so that is the easiest picture. You can, everybody, you have a pen and a paper, you can draw the picture yourself. Okay, the curve is inside circle. You have the x-axis and a circle touching the x-axis and above the x-axis, let us say. So the graph that defines the circle will be always, or the function we define circle will be always smaller than the the function defines the curve because the curve is inside it. So y coordinate will be bigger. Okay. So that's what I repeat. At the point P, the intersection of the curve, C and gamma, both are the tangents coincide. You can then perform a rotation about the point P so that the tangent coincides with the x-axis. And the circle lies in the upper half plane. Okay. As before, seen that sufficiently small epsilon positive, both the curves are represented by graphs psi from minus epsilon plus epsilon to R2, such that actually R here, such that F1 of 0 equal to F2 of 0, 0, 0, P. The P is, I am assuming, 0, 0. The derivative of F1, derivative of F2 is 0. That means the tangent is horizontal. Now we apply the lemma. Okay, so this is R here, not R2. Is that clear? How to compare whenever two curves are touching, how to compare the kappa of these two curves at a point wherein the two curves are touching. So this is what I have done now. So that is the local geometry. We are now going to present an easy proof due to Robert Osserman. Okay, not very old, you see, 1985. Okay, the following result. 4 vertex theorem, okay, due to Knesser and Mukhopadhyaya. So let me first state it and then explain it. Let gamma be a simple closed regular curve in the plane. Simple closed, okay, regular curve in the plane. Then its curvature function kappa has at least 2 local maxima and 2 local minima. So there are 4 points wherein this extremum takes place, or what you call as curvature function. Therefore, it is the stationary point of the curvature. You see, for a smooth function, local maxima, local minima are attained. Why? Then kappa dot must be 0. Okay. Kappa dot may be 0. The thing may not be a maxima or minima. It may be an inflection point. So this theorem says a stronger conclusion. There will be exactly at least 2 local maxima, 2 local minima. At all these points, kappa will be 0, kappa dot will be 0. So there are at least 4 points wherein kappa dot is 0. Okay. That was the conclusion of Mukhopadhyaya, way back in 1909, almost more than 110 years old. 110 years old, maybe even more than that. This Mukhopadhyaya is not just a name. He worked in Calcutta. He was a downright Indian. This is long before the independence. Okay. So what he proved is, for a convex curve, convex simple closed plane curve, there are at least 4 vertices. Vertices means kappa dot is 0. That's what he proved. And the proof of that is there in the book also. Okay. Of course, in the book, there is a polished proof which looks much simpler, whereas Mukhopadhyaya's original proof is not all that simple. But the idea is the same. Later, Knesser generalized this result to this theorem. That's what, okay, the theorem here that I have quoted. So as it appears here, it is a Knesser's version. This is much more general because it does not assume convexity at all. The curve need not be convex. By the way, I defined what is a convex curve last time. Do you remember that? A convex simple closed curve is nothing but the interior region must be convex. Okay. So like ellipse and a circle, of course, or some weird thing, but it has to be convex. So there are not many examples. If you take piecewise smooth curves, then there are many examples like convex polygons. So that's what we are studying. Here, we are not allowing piecewise smooth. It's entirely regular curve. Okay. So smooth, so it's a manifold. It's a one-dimensional manifold. Okay. One can allow that also, piecewise smooth also, but then what is the meaning of local maxima, local minima, etc.? You have to be careful. At all those points wherein the function, wherein the curve is not smooth, they are all taken as vertices. So in some sense, if it is not a regular curve, the proof becomes easier. You understand? Because you have to prove 4 vertices, all the points wherein the function is not smooth, they are already counted, right? So that makes it easier for you. So the best thing is to prove it for regular curve wherein there are no corners. So corners just you can't add as vertices now. So vertices of this curve will be those wherein kappa dot is 0. So that is something additional you have to prove. Okay. So let us stick to regular curves now, not piecewise smooth curves, as compared to the earlier theorem, namely the isoperimetric inequalities. Okay. You got it? Any questions? So I have repeated here, whatever I repeated. Original version of this theorem, which goes under the name 4-vertex theorem, due to Mukhopadhyaya 1909, states that if gamma is a convex simple closure curve, then the derivative of the curvature function vanishes at least at 4 points. Okay, such points are called vertices of the curve. The terminology is borrowed from optical theory. Why he was interested in? So this is a physical problem at that time. Okay. C.V. Raman spent a lot of time in Calcutta also. Okay. So it was those days wherein a lot of, there was no difference between any scientist, will be mathematician, astronomer, or a physicist and so on. They did many things together. So we may read a proof of this version in the book. This is what the simpler version, there is a simpler proof in the book. So let us go ahead now, okay? The hypothesis in the above theorem is weaker and the conclusion is stronger than the original version due to Mukhopadhyaya. Now, this version is due to Adolf Kneser. It's 1912. See, 1909 was Mukhopadhyaya. Kneser made it in this version. The proof that I am going to present is much more simpler than Kneser's proof, and that is due to Osserman. Okay, it's 1985. So this is all historical comments. Now, the central idea of Osserman is the following. Maybe it is not Osserman's idea, it was there earlier, but they did not exploit it to the full extent. The basic idea in the proof is so-called circumscribing circle of a simple closed curve, gamma. So C is C gamma. C gamma means what? It is the smallest possible diameter. Okay, you have to choose all those circles with the smallest possible diameter such that gamma is contained inside the interior of C. Okay, note that this is not the same as your school geometry word circumcircle of a triangle. Now, circumscribing a regular polygon is something different than circumcircle of a triangle. Circumcircle is defined as a circle passing through the endpoints, passing through the three vertices, right? You can test it that why it is not equal by simple example. Okay, here is an example. CT is this one, whereas the C prime is the circumscribing circle. Okay. CT, the smallest one, which contains T, is just, this is the diameter and that is the center. Take the largest side as the diameter. So that is CT. There cannot be anything smaller than that, because diameter of the triangle, okay, the largest side of the triangle must be inside, and I have made it into diameter of this circle. So this circle CT is the circumscribing circle. This is the circumcircle. So there is a difference here, okay? So don't get it confused. The circumscribing circle is defined as the smallest circle, smallest in the sense what? The radius is smallest, or you can say the diameter is smallest, all right, which contains the given curve. In fact, I would like to add this one, namely, this concept is available for any compact subset of R2. Compact means what? Closed and bounded. Take any closed and bounded subset of R2, this is possible. Okay, whatever we are going to do, till we come to the kappa. Okay, you don't use the property that gamma is actually a curve. All that you are using is that it's a compact set. Let us keep that one aside. So let us concentrate that now. We have defined what is the meaning of the circumscribing circle. Okay. We make the following observations. First of all, we need to prove the existence and uniqueness of the circumscribing circle. Remember, one of the objections for Steiner's proof of isoperimetric inequality. In that proof, we never proved the existence of a minimizing, a maximizing, an optimizing curve. Okay. So we are not going to fall into that trap here. We are going to prove that circumscribing circle does exist for every compact set. All right. So instead of every compact set, I am just using it here only for the given curve. Doesn't matter. Okay. Let us see how. Since gamma is a bounded set, see, I am only using this. There are circles C prime such that gamma is contained inside the closure of IC prime. That is the meaning of bounded set, right? To fix one such. I don't care how big it is, how small it is. Fix one such. So start with a circle such that your curve gamma is completely contained inside interior of C prime. No problem. It follows that the radius of C, if C exists, okay, I am not yet proving that, E has to be less than or equal to radius of C prime. Because once you have a circle like this, we are looking at a minimizing one. Okay. So the minimal one has to be less than this one. Therefore, you don't have to worry about any circle with radius bigger than the radius of C prime. That is the first observation. You start with one circle, then you can take only those which are smaller than that, if at all. All right. So let D be the closed disk with center as C prime and radius double of that. If C prime, let us say, for example, for sake of definiteness, origin is the center. Okay, you can always do that anyway. Origin is the center. The radius of C prime is R prime. Now you take a circle of radius twice R prime. That's all. Okay, take twice I prime. Let D be the closed disk of radius double of that. That's what that is D. Any circle containing gamma and center outside D will have radius bigger than the radius of C prime. Because once you are outside D, you have to come all the way across to even to hit C, you have to take that much of distance. Then there you have to go contain gamma also, so it will be little more. So anything which is outside, the center is outside, those circles are out of question. They are also outside our purview. So we can concentrate on one single large disk. What is that large disk? It's not very large, it's twice the radius. Okay. So the entire plane is now cut down into a compact subset D. Okay, you don't have to go outside this one. Your curve is here. You don't have to search for anything other than this one. All points will have radius inside D. Sorry, all circles, what we are going to consider, they are inside D. Okay, the centers will be inside D. Okay, so to hunt for C, because we have not proved the existence yet, we need to consider only those circles with their centers inside D. Okay. Okay, slowly we will sharpen. So this is what I have done here. Picture gamma is the original curve. C prime is a circle which contains it. D is the same center but radius twice that one. This is radius of C prime and it's twice that. So now I am going to look at all the circles which center is inside D. Okay, amongst them, my C must be one of them, right? So let us see what it is. Now define the function f from D to R as follows. Fx is the maximum of the distance between x and gamma, x and y inside gamma. The maximum of the all. Start taking x to y, y1, y2, y3, etc. inside gamma. Take the supremum, because there is infinite set. Take the supremum, but gamma is a closed bounded set, single x is fixed, therefore the supremum is attained. Why? Because the distance function is a continuous function. Okay, x is fixed, it's a function of y on the compact subsets gamma, therefore the supremum is attained. When the supremum is attained, it's called the maximum. Okay, so this is elementary real analysis. All right, clearly this is a continuous positive function and hence attains its infimum for us. Now next step is the maximum itself is a continuous function of x now. See, in this definition, x was fixed, fx is this one. For that, we do use the continuity of D, the metric. Okay, what is D? Is just modulus of x minus y. Things are happening inside R2, so norm of x minus y. Okay, so now the maximum of this one itself is a continuous function you have to use. Okay, so that's also elementary exercise in the real advances. So clearly, this is a continuous function, and this is always positive. No matter what you take, okay, gamma is a closed curve, it's not a single point. If gamma is a single point, this can become zero because you can take the same point. Okay, if gamma is not a single point, this is where I am using it's a curve, that's all, instead of just a compact. The moment it has at least 2 points, the maximum distance from x to y, this is going to be a positive function. Okay, so this is a positive function. Where I am going to take this one now, x is inside this compact set. Therefore, its infimum is attained. That becomes a minimum. Okay, infimum is attained. Infimum will be positive because it's attained. Otherwise, infimum of a positive function may be zero. It is attained is important here, so it is a positive thing. For some q inside D, attained means what? It is achieved at its value of something. X equal to q, it will be equal to the infimum. So it's mean now. Okay, so we have found a point q. What is the property of q? Look at d of x comma d of q comma y. Okay, this fx is the maximum there. Okay, amongst all these, this q is such that for if you change some, if you vary q prime, those will have larger values. Okay, so this is max and min. Okay, this is like a minimum min max principle that I have used here. Okay, take q belonging to D such that this is infimum, this is the minimum. Now I want to say that q, okay, as radius, as center, and r, which is the minimum distance, as the radius, that circle is precisely the circumscribing circle. This is the statement now. Okay. After all this, the function and all this observing, this is the claim. Now what we have to prove? We have to prove that this circle C contains gamma, and anything which is smaller than any circle which is of smaller radius than that will not contain gamma. So two things you have to prove. Okay. Clearly, gamma is contained inside the region C. Why? Because what is the meaning of gamma is contained inside C? Distance from Q to Y should be less than or equal to R. What is R? R is supremum of all these. You see, it's the infimum of supremum, but for each of them, it is supremum. Right? So, this is maximum distance. So, all the distance dxy, where y is dqy, where y is in gamma, is less than or equal to R. Less than or equal to. In any case, they are inside C. So, this is easy to see. If you take a circle with radius smaller than R and the point contained inside D, that will mean that f of that point will be smaller than this one. Right? That's a contradiction to the infimum value. Q is infimum value. Therefore, if you take any r prime less than R, it cannot contain gamma. So for this, I have to just look at only all those points inside D now. If I go outside D, obviously they are bigger. That is the first part. Okay. For then the center P of such a circle inside D, this FP will be smaller than or equal to R prime, and R prime is less than R. That's a contradiction.
Sir, can you explain again why gamma contained in the inside the region of C?
Hello?
Hello?
Tell me.
Can you explain again why gamma is contained in the inside region of C?
The distance between the center and the point is smaller than the radius. That is the claim, right? That will mean that it is contained in the interior. Take a point y inside gamma. What is q dq? Dqy. What is dqy? What is q? Q is a point wherein infimum of all these effects are there. So FQ is by definition maximum of all dxq's. So FQ is nothing but dqy. dqy is bigger than or equal to all these things. That means what? Not clear?
Okay, sir. Okay.
So if still you have problem, you take a curve, okay, take a circle two different ways. One is that it is not contains gamma, and one it does not contain, it contains gamma. Then verify what happens to that, the points. That way you can understand what is going on. So you may have to draw 1, 2, 3 such pictures and see that this is the way to approach the circumscribing circle.
Okay.
But this is totally elementary. There is nothing here other than triangle inequalities at the most for the distance function. Okay. So we have defined the circumscribing circle as the circle with the shortest radius and containing gamma. Okay. And we have shown that this exists. And it is unique. Okay. So let us see why this is unique. Uniqueness part we have not yet seen. Then only we can say the circle. Okay. There may be many. So here is the proof. This is also easy. Take C2 to be another circle. Radius has to be R only. It cannot be smaller. That we have seen, right? But different circle. So there are two circles of same radius. Center has to be different. P not equal to Q. Both P and Q are inside D. That part is fine. Okay. Intersection of two circles. Okay, the inside region contains gamma. That is the assumption, right? That gamma is contained inside both of them, right? But what is the intersection of any two circles? It is some lune, right? The lune, diameter of the lune is always what? Circles are of same radius. Diameter of the lune is always less than 2r. Okay. Take the take the chord joining the 2 points of intersection. Okay, that chord will be smaller in radius, diameter than the diameter of the circle. If the diameter of circle, if it coincides with that one, the 2 circles will be the same, right? Because you are taking 2 circles of same radius. Okay, therefore I have a circle of smaller radius containing gamma. That's a contradiction because R is the minimum. Okay, so there cannot be any other circle. There will be a unique circle like this. Okay, so this proves one first part, namely one observation. Okay, so I am giving you these details. Nobody writes down these details. They just write this a unique circle exists and go ahead. The second observation is C must intersect gamma. What we have seen is, what we have so far observed is C is in the interior of gamma. If it does not intersect, obviously you can take a shorter circle, a smaller circle, right? Because this R is nothing but FQ. Remember, Q is the one of the values, minimum value of all R. R is FQ. FQ is what? Maximum of DQ by the very definition. Okay. So if this is maximum, it is attained, C intersection gamma must be non-zero. That point must be there already. Okay. So this is very easy to see. The third thing is C intersection gamma is not a proper subset of any semi-arc of C. What is the meaning of semi-arc? Take any diameter, take the part of the circle on one side. Any diameter cuts it into 2 semi-arcs. Okay, half the circle, semicircle we say. All right. The intersection points will not be contained on one side of any diameter on the circle. That is the claim here. Strictly on one side. You see, it can happen that they are only including the diameter. That can happen. For example, take an ellipse. Okay. Take an ellipse. And what is the circumscribing circle for an ellipse? Hello?
If x square by a square plus y square by b square equal to 1.
Don't use equations, use geometry. It's a major axis.
Major axis.
Major axis will be the
Axis.
diameter.
Yeah.
Okay. You can put it whichever way you like. Yx square plus y square and so on. All right. The major axis will be the diameter and the center will be the center. That circle is the circumscribing circle. Now, what is the points of intersection? Exactly the 2 points on the diameter. Right? So they are contained in both the semicircles. So this is the only situation where it can happen, is the claim here. Okay. I mean, this can happen simply like, suppose I take a triangle, that can also happen. I have shown you. Okay, but triangle we are not allowing, so we can make a small curve like that, not necessarily ellipse. Slightly change the elliptic shape, slightly away, you can have that. So there are such possibilities, but only one side including the endpoints. So that is not a proper subset. See, C gamma is not a proper subset of any semi-arc of C. Okay, It is not on one side. Both the points may be there. The full arc will be there. Okay, full semi-arc is allowed. If you don't allow one of the points, the end points, okay, for example, any one of the end points, then it is not possible, is what I want to say. Okay, so this needs a slightly, unusual kind of geometry, but it's again geometry, purely geometry of school. Okay, so how do you do that? For suppose this happens, let PQ be the diameter of such a semicircle. In particular, this means that C intersection gamma does not contain both the points of PQ. If it contains both the points, then it is a full arc you have taken, right? So at least one of the points is not there. Therefore, you can slightly rotate this semi-arc, the entire circle, a PQ, slightly move it up or down, okay? By semicircle, we can assume that C intersection gamma does not intersect one of the semicircles, say S. One intersect one of semicircles, say S. Now, new point is now PQ are not in the, both PQ are not inside C intersection gamma. So whole thing is on one side only. The other side is not intersecting S at all, intersecting C at all. Okay, the semicircle S does not intersect C intersection gamma. Okay, we want to say there is a contradiction. This cannot happen. Why? Because what happens is now the entire S intersection gamma itself is empty, because if intersection with gamma, then they will be inside C intersection gamma, right? So S is a part of C. Okay, so if S is a closed set, gamma is a closed set, its distance between these two disjoint closed sets is a positive thing. The distance between S and gamma is a positive. Okay, distance between any disjoint two compact subsets, okay, closed and bounded subsets, is positive. Okay, they are both closed and bounded subsets. Now move the circle C by distance less than this d by 2. This d is d by 2 in a direction perpendicular to the given diameter, whatever you have fixed right now. Okay, slightly move it towards this gamma. Okay, the circle will go, then you can avoid the entire gamma. The circle will be the same circle, moved slightly, okay, in the direction perpendicular to PQ. Okay, so its center will change. This time what happens? All the points which are inside the circle, they will come inside the circle, not on the circle, into I gamma. Okay, the new position of C prime, new position, the circle C prime will be such that distance between C prime and gamma itself will be positive. Therefore, it will be contained inside IC gamma, contradicting the minimality of the radius of C. Once you have such a C prime which does not intersect gamma at all, then there will be a smaller thing because of our observation 2. Okay, observation 2 is just here. So that's a contradiction. Okay. Yeah. Once again, there is some problem with this. So I'll have to do something here.
Sir, is it a technical problem, sir?
Hello?
Yeah, is it a technical problem, sir?
The file has stopped responding.
Okay.
So I had to
Yeah, we can unshare and share, sir, again.
yeah, now I think the
Hmm.
file is okay now.
Working.
Hopefully, I
Yes, it
opened
works.
another one.
Yeah, it is working, sir.
It's already working.
Yeah, yeah.
No, it may be older one. Let us see. Do you get a okay, okay. Now it's okay.
Yeah, it is coming, sir, actually. Yeah,
What do
for
you see?
example, now lemma 1.39 is there.
Okay. Now this is what I want. Yeah. So there was some confusion about which file I'm using. Okay. So here is the picture wherein this entire curve gamma was inside this semicircle P to Q intersection, gamma intersection. See this point, all these points were only on this part of the circle. Okay. That means what? This semicircle, upper semicircle S, does not intersect gamma at all. So this distance will be positive. So I just move it slightly, this one slightly below. Okay. So to get another circle, see this circle is smaller now and it will contain gamma. Okay. So if both the points, these points were in the inside a circle, inside the gamma, then I couldn't have done that. That was not possible. Okay. The moment it is only one side, strictly one side, you can just move the circle slightly parallel to perpendicular to this direction, perpendicular to the diameter, and then that will be completely contained the circle in the interior. Therefore, you can take a smaller circle. All right. So the conclusion here is that C intersection gamma, first of all, is non-empty. It's not a proper subset of any semi-arc of C. So that is the conclusion. The next thing is that simpler. C intersection gamma can be contained in some closed semicircle, in which case it contains both the endpoints. Okay. This I have already told you. For example, in the case of ellipse or slightly modified versions of ellipse. So such things are possible. Okay. So these are the observations. Now we come to Osterman's idea. Okay. Let us now look at path connected components of C intersection gamma. So this is pure topology now. Huh? If any component is not a singleton, a path connected space means what? Given any 2 points, there is a path, right? The image of a non-constant path is always uncountable. There will be lots of points there, right? By intermediate value theorem. Therefore, what you have is that any component is not a singleton, then it contains an arc of C, because the whole thing is, see, what I am taking C intersection gamma is a subset of C, right? The whole thing is a subset of C, and component, it will be arc, there will be small arc between any 2 points which are a connected part, small circle of C of positive length, along which, if you have an arc of a circle, what is the kappa? Kappa is a constant 1/r there, right? Kappa is constant 1/r for the circle. But now circle is the same as the gamma, curve gamma at that part. intersection of C intersection gamma is a curve, part of a curve, one of the components. It is on gamma also, it is on C also. So if it is a circle, the kappa is a constant 1 by r. So its derivative is 0 on all those points. Therefore, there are infinitely many vertices there. Right? K intersection, K is 1 by r, derivative of K is 0. Right? Not only that, all those points, because constant, they are both maxima and minima. Maxima is local maxima here, right? Maxima means local maxima after all. They are all local maxima as well as local minima. For a constant function, all the values, all the points are local maxima minima. So there are plenty of them. We want only 4 of them in the theorem, right? So we can assume that all the intersection points are only singletons. Okay? That is the case which is interesting case. Other case is obvious. It can occur. Okay? A circle, a smooth closed curve, part of it may be circle. It need not be circle all over. In that case, this will happen, and we are through. Okay, so we may assume that all components of C intersection gamma are singletons. In particular, it follows that C intersection gamma has at least 2 components. Okay, she has at least 2 components. If it's one component, it will be a singleton. Then P says, this says there will be a smaller circle, right? The observation 3 says it will be contained inside, one single point is contained inside a part of semicircle. That is not possible. It just must have at least 2 points, and that can happen. Example is ellipse. Okay, the worst case can happen, that is ellipse. Do you know why ellipse is the worst case, whereas the circle is the best case here? If the curve is a circle itself, every point is a vertex, because kappa is a constant 1 by r. It's a very peculiar example. Just make it an ellipse. Okay, ellipse is the worst. It will have only 4 vertices. Elementary exercise that is done in your book. Please go through that. For the ellipse, there are exactly 4 vertices. Okay, easy proof, elementary computation. You have to parameterize the ellipse and then a cos theta, b sin theta, whatever, and compute it. All right. So it can happen. So we can't exclude that case, but it cannot have one single point. Okay. In particular, it follows a C intersection gamma, at least 2 components. They are all points now. Finitely many points will come, of course. Okay, but I don't care whether there are finite or infinitely many points. So we are not, we can prove that it's finitely many points, but we are not interested in that. Okay. Now, this is clearly Osterman's idea here. So I am stating it a separate lemma due to Osterman. If the intersection of circumscribing circle and the simple closed curve gamma has at least n components, we know that n is bigger than or equal to 2. Okay, this is a case we are interested in, right? So suppose we assume there are at least n components. Osterman doesn't even assume that they are single points, but we are assuming it for the proof of the theorem. So this lemma is much more general. just n components, n greater than or equal to 2. Then on the curve gamma, there are n distinct points P1, P2, Pn, at which kappa will be bigger than or equal to 1 by r, and n more distinct points Q1, Q2, Qn lying between Pi's such that kappa is less than 1 by r. The first part is greater than or equal to r, 1 by r, less than 1 by r. So what is the meaning of lying between? See, you have to trace the entire thing in one single fashion, either counterclockwise or clockwise. See, you are going through a circle of radius r. Okay, that is all fixed here. And the curve is inside the circle. It will have to touch the circle at least in 2 distinct points. So all these things we have done already. So what you want to do is, you want to pick up points on the curve, tracing it in, let us fix it, tracing in the counterclockwise direction. Okay. So how do you do that? Start with any point wherein the statement says wherein kappa is greater than or equal to 1 by r. Go to another point, go to another. This way you can pick up n points, and then between P1 and P2 you can pick up a Q1, P2 to Q2, before P2 to P3 if you go, you will get a Q2 and so on cyclically. So that is the statement. At Pi's, the kappa is greater than or equal to 1 by r. At Qi's, it is strictly less than 1 by r. Okay. Suppose you assume that this result has been proved. I want to say that the proof is complete. Proof of the Knesser's Mukhopadhyaya theorem will be completed. Okay. There will be 4 points wherein kappa has derivative of kappa must be 0. Maxima, minima will occur. So that is the stronger statement here that I want to say, that once you prove this one, it's completely linear real analysis. Assuming this result, it is elementary real analysis to find local minimum between Pi and Pi plus 1 and a local maximum between Qj and Qj plus 1 cyclically. Okay. So why? Because what are Pi and Pi plus 1? At Pi, the value of the function is a smooth function. Kappa is a smooth function, real valued function. Remember that. Okay. Of the parameter. So this is where you have to use a parameter. Explicit, using that explicit parameter is not at all necessary here because we are not going to do any computation. Okay. So at one point at P1, it's bigger than or equal to r. And again at P2, it's bigger than or equal to r. But at Q1, it is less than 1 by r. So draw the curve at 2 points. Okay. P1 and P2. The value P1 and P2, y coordinate, you can say, function, okay, kappa. It is bigger, it is greater than 1 by r. At in between at Q1, it is smaller. Okay. Therefore, between P1 and P2, there must be a local minimum. Right? Between P1 and P2, there must be a minimum actually. So it will be a local minimum. Exactly same way, once you have come to Q1 to Q2 now, at Q1 and Q2, it is less than 1 by r. In between, there is a P2, which is bigger than 1 by r. Therefore, in between, it may not be P2, it will be some other point. The value of the function must attain its maximum. Right? This Rawls theorem is all that I am using. Exactly not Rawls theorem, because their endpoints may not be equal, but you can reduce it to Rawls theorem. Is that clear analysis? So once you prove this, what you will get between P1 and P2, there will be a point which is local minimum. Q1 and Q2, there will be a point which is local maximum. Okay, it may happen that local maximum, local minimum, they are all equal, but I don't care. That can happen because the curve itself may be a circle, part of a circle. Okay, it is only question of finding the points, not the value of kappa there. The value of kappa bigger than 1 by r, less than 1 by r is used here to show that there will be enough maximum points and local maximum and local minimum. Okay, so I have to prove this lemma, okay, Osterman's lemma, which is again very much geometry. Okay, like school geometry, you will see little more complicated than school geometry. You don't see school geometry this much anyway. So it is geometry. So here is a picture here. Gamma is the given curve, which is thicker than all other curves in the picture. Okay. P1 and P2 are 2 points. Okay, wherein what is happening? Kappa is bigger than or equal to 1 by r. Okay. Kappa has to be bigger than or equal to 1 by r because P1 is a point of intersection of the curve gamma and P1. By lemma 1, if you pick up such a point, P1 it is the intersection of C and gamma is completely contained inside the interior of C. At all those points, the kappa of this one will be bigger than 1 by r. Okay, so P1 and P2, I have picked up 2 points which are on the intersection of these two circles. Why I can have 2 points? Because it has at least 2 connected components. That's why there are at least 2 points. Okay. If there are more components, I can pick up all those points. N of these points I can pick up. Right? All of them intersection point, here one, and so on. It depends upon how many components are there. In each component, I will pick up one P1, P2, Pn. At all those points, 1 by r is smaller than the kappa of the gamma. So that is picked up. So first part is over, namely the existence of there exists pi local maxima. Sorry, is this one. The kappa is bigger than or equal to 1 by r. So this part is over. Now I have to show that between those points there are points on the curve, okay, at which kappa is less than 1 by r, strictly less than 1 by r. So this is where you have to work a little hard. Okay. So how to find the point Q? So it is enough to prove it for one pair of points P1 and P2. Again, I will repeat it, P2 to P3, P3 to P4, and so on. Okay, so this picture shows only the how to do this one, P1 to P2. Okay, look at the part of the curve traced in the counterclockwise sense from P1 to P2. Let us call it as part of the curve, which is gamma 1. Okay, what happens to this curve? You see, the circle, this is the circle, it is touching here, okay, this C1. This rest of the curve must be inside the circle. It may be part of its circle, that's allowed, but that will be too easy for us. So we shall assume that it's actually inside, it goes inside this part, inside the circle. Okay. Right? Similarly, when you come here, this part will be also inside a circle. But it will be inside this, we join this chord it will be, this portion will be actually in this area between this chord and this part of C1. Why? Because look at the tangent here. Okay, this tangent is not perpendicular to P1, P2. P1, P2 is not a chord. Maybe it is perpendicular. Maybe it is perpendicular. It doesn't matter. Okay, but curve has to be here. It cannot be on this side, right? It's a tangential here. The curve has to be inside this one. It cannot cross the perpendicular. At the most, it may be perpendicular when this is a diameter, right? So it has to be here. Therefore, portion of the curve, I have shown all of the curve, but once it enters, it may go like this and intersect gamma itself, intersect P1, P2 itself. That's allowed. You come like this, go like this, go like this, that is allowed. Okay, so it lies here. That is one part of this one. So that's what I wanted to say. So specifically, start with, consider the smaller arc C1 of C between P1 and P2. Let gamma 1 denote the part of gamma between these 2 points. Since gamma 1 and C1 are tangential at both the endpoints, some part of gamma 1 intersect the interior of I am putting interior of what? PQC1. Okay, so P1, P2 in the diagram it is P1, P2. P1, P2, C1. This is the curve. It's a curve now. So this is a sector of this circle and the chord. Okay, it must be inside that one, where this denotes the union of the chord PQ and the arc. Okay, so sometimes I say P1, P2 and some PQ. So that is, sorry for this notational difference here. Let Q, so this is P1, P2 here. Q belongs to gamma 1 intersection I P1, C1. Okay, so you take I interior of PQ, C1. That means inside there must be some point here, Q, right? This Q1. This Q1 is on this curve, but inside this one, if you take a point, in this area of the circle, okay, then if you, sorry, this is my Q here, Q1 is something different. Then you take the circle, the unique circle passing through P1, Q, and P2. Okay, the passing to P1, Q, and P2. See, given any 3 points which are non-collinear, there is a unique circle passing through them. By moving Q slightly away here, you can assume that it is not on this chord, that's all. It is inside here, that's all. So they are not non-linear. P1, Q, P2, they are non-linear. So there is a unique circle. That circle is of radius bigger than R. Elementary geometry. Okay. This circle is of radius bigger than R. Now what I'm going to do? I fix this circle. I forget about these points. I start moving it parallel to this P1, P2, parallel to this chord. Move it till it becomes tangential to the curve gamma. Okay. The point that it intersects, it must be tangential, because here the angle is different, positive angle here between this chord and this tangent. The angle here is, we can say, negative. Angle here is positive. So the angle changes here. So somewhere the angle must be 0. Angle between this chord and the the tangent is 0 means the chord is parallel to that one. So you keep moving here, this tangent here is in parallel to that one. That's why you got that. So you keep moving here till this circle becomes, the turning point. Okay, so this will be tangential to that. Now the angle between these two are what? Equal. So that is tangential. So this is what I have written down here. Let C2 be the circle passing through P1, P2, and Q. The radius R2 of C2 is larger than R, and hence 1 by R2 is written 1 by R. Okay. Let now we denote the vector represented by the chord PQ. Consider the smooth function V gamma dot X. This hat I am using from your book, this notation. This is angle between V and another vector here, gamma dot. Okay, tangent vector. This angle, okay, angle measured from V to gamma dot as x varies over this x I have put here, it is over gamma 1. Okay, the point. Let P and Q, at P and Q, it takes different signs. That is obvious here. Angle, the tangent here, okay, measured from here to there, if this is positive, here it will be negative. So at some point, it must be 0. Okay, so that is what I am using. Again, intermediate value theorem here. So coming here. So by intermediate value theorem, it must be 0 at some point Q1 belong to gamma 1 intersection this P1, P2, C1. This means, this just means that at gamma, at that point Q1, x equal to Q1, gamma dot is parallel to PQ. Okay. Now move the circle C2 by a translation parallel to PQ so that it passes through a point Q1 and call this the new circle. C3 I have done, I think in the diagram this has become C2. Okay. There is, okay, C3 is there. C3 is this one, yeah. This is the position of the circle, okay, wherein it has become tangential here. Yeah. So it follows that. So now move the circle C2, translation parallel to PQ. Okay, I have to be parallel to PQ, it's not perpendicular to PQ, it should be. So that it passes through Q1 and call this new circle C3. Okay, it follows that some portion of gamma 1 around Q1 will now lie in the loon defined by C3 and C. See, I started with, again, the picture. The picture is only modular, is only a guidance, but you can do without picture also. So some portion of this, once it's tangential, it started with some both of intersecting. Now it must be on the other side of PQ. So this part, this is C1, C3, that was C1. They intersect somewhere. This portion, small portion, must be on the other side. Right? This is tangential here. By our lemma, the curvature here of this curve at this point must be smaller than this 1 by R2. The 1 by R2 is smaller than 1 by R. At this point, is smaller than 1 by R2. So that is smaller than 1 by R. Okay. Here I have actually shown that it will become negative. It may not be negative. It may be just touching like this and it can be still bent on the other side itself. Okay. Like a parabola is touching a circle, can be outside this one. Or even a straight line here, okay, wherein the curvature is 0. Okay, it need in my picture it's actually negative, the other way around. That may not happen, but at once it is like this. Okay, outside the circle. For this circle, it's outside. This circle is radius 1 by r2. Therefore, the kappa here is smaller than 1 by r2, which is smaller than 1 by r. So take this point. This point is between, you start from P1, go like this, Q1, and then P2. Repeat this process to get Q2, Q3, Q4, and so on. Okay. So sorry, there are some typos and incompatibility between notation here and what I have done here. So this PQ is actually P1, P1, P2 here, everywhere. Okay, this Q is Q, correct. Okay, so I have to do some corrections here. Okay, so that's a proof. So kappa at Q1 is less than 1 by R2. That's less than 1 by R. Strictly less than 1 by R. So here is an equality. Okay. Okay. The simplest curve other than circle is ellipse. So start verifying it for that. Okay, all these thing, what is happening, you will see that. Okay, this proof will tell you that between the two points of major axis, there is some point wherein the kappa has to be 0, dot kappa has to be 0, minimize it. So minimum will occur. The major axis, it will be maximum. So here is minimum. So there will be 1, 2, 3, 4 points like this, which are maxima and minima for the function kappa. Okay. Of course, in the case of ellipse, you can actually write down and find out the exact points also. Namely, they are the intersection of the major axis with the circle and with the ellipse, and the minor axis with the ellipse. So this theorem only shows that there exists. It doesn't give you a formula because gamma is not given by formula. Whenever you give gamma explicitly, maximum, when you compute maximum minima, it's a different thing. If you cannot compute it by hand, you can put it in nowadays. You can put you can use some programming, and the computer will do it. So that is always there. Huh? Okay. So any questions now? What is the time now?
Time.
Huh?
You took
6:15, sir.
What is the time?
6:15.
6:15, sir. You took more actually today.
Okay, so this is the last lecture anyway for this.
Yeah,
part.
that's what I also. That's the reason I.
So if people have any questions, so anyway, tutorial is also geometry now, right?
Yes, sir.
You can take